the filled-in answer version is also on there for you to print out. You're welcome to print it. Have it in your notebook. Have it available. Okay? So, a couple of things about roots and radicals. We hit some of it last week. We talked about how when we have our radical sign, okay, we have the number underneath. It's called the radicand. It's just the number underneath. We have, I often will call it my root sign. It also has a special term called the index. If there's nothing written there, what number is it? 2. Okay? It gives us the instruction key to tell us how many of the same number that we need to have for it to escape. Okay? So, as we move forward and we start simplifying, you guys had a simplification homework sheet. So when we have the square root of 100, like it's up there, 100 is really 10 times 10. I could also write it as 10 squared. So we talked about, it tells me how many I need to, I have to, this can escape. Or if we have it written like this, when the index matches the exponent, it erases everything. So a couple of different ways visually for you guys, however you want to figure it out. Work that way. So either this way, I had 10, it escapes as a 10, so this gives me 10. This erases the whole thing, gives me 10. Okay? When our radical simplifies completely, it is called a rational number. Okay? Remember all the way back to those circles that we did? Okay? So we had our counting numbers, whole numbers, integers, rational numbers, and then we had irrational numbers. Okay? So when it simplifies completely, it's called a rational number. When it does not simplify completely, and you have something left over, these were those square roots that were over here in the irrational numbers, right? It's irrational. So if you're asked to sort, like, is it rational or is it irrational? If it simplifies completely, it's rational. If it has some left over, it's irrational. Okay? So when we have radicals and we're adding and subtracting them, we get to, they're not a variable, but we think of them in the same terms as a variable. So I have variables at the top. We have 2x plus 3x. Are they the same family? Yes. Same family group, we can add them together. If I have 2x and 3x squared, are they in the same family group? Are they like terms? No. So we can't combine them. So in the same way, when we look at a radical, because it is all information, this is saying I need two groups of a certain number. So if I'm going to add them, they have to have the same number of groups of the same number to be the same family. So in this case, I have a square root of 2 plus 2 square roots of 2. So I need 2 of 2. I need 2 of 2. These are the same family in the same way if I had x plus 2x. If I had x plus 2x, it would be equal to 3x, right? There's an unwritten coefficient of 1 here. So again, we add our coefficients in the same way if this were x plus 2x, we have 3x. And we have our radical stays the same. Okay? In this case, I need 2 of a number 2 and I need 2 of a number 3. Are these the same families? No. These cannot be added. Okay? So when we add radicals, both the index and the radicand have to be exactly the same. So I would need square root of 5 and a square root of 5. Ooh, it's a bad 5. It has to match exactly. And then all we do is add the coefficients. So in this case, it would be 2 plus 4 would give me 6. This is the same as 2x plus 4x would give me 6x. My x just happens to be the square root of 5. Okay? Adding and subtracting. Same way. Okay? There are several rules. So we simplify all of the radicals first. In this case, Cube root of 8 tells me I need 3 of the same number. Cube root of 8 is 2. 2 times 2 times 2, in that way. So you would simplify all your radicals first, and then you're going to find the ones that match. So here I've got a cube root of 3, and it matches this cube root of 3, so our green terms can be added together. 4 plus 3 is 7, and we leave it as cube root of 3. Okay, I'm going to find the next ones. I've got square root of 2, square root of 2. These match exactly, so I underline them both in red. 2 plus 1 is 3, so I have 3 square roots of 2. And then I have this cube root of 8 by itself, which actually is the number 2. So when we're simplifying, we're just combining like terms, just like we did with variables. You have to find the matches that match exactly. Okay? So when we multiply them, so for addition, both the index and the radicand have to be exactly the same, just like with a variable. Now, if we were looking at variables with multiplication, I can do x times x squared, right? We can do that because we know that the base is the same. So even though the exponent is not the same, our base is the same, and we end up with x cubed. So for radicals, as we move forward, the index has to be the same. So I can have the square root of 2 times the square root of 3. My radicand is not the same, but I need the same amount in the groups. And that's what we kind of talked about that with pizza, like your slices have to be cut at the same size to be able to combine them. So when we look at multiplication, this index number is the one that you have to match up. I need groups of 2. I need groups of 2. When I need the same number of groups, then I can simply combine and multiply the numbers underneath. And this one down here, I need a group of 3. What's the number for this one that's empty? 2. I need a group of 2, and then I need a group of 5. So I can't combine any of these. None of them match. So none of that can be multiplied together. Okay, so think of it in the same way that if we have a variable where we actually multiply our coefficients and then we multiply our variable portions. So in this one, I need a group of 2, I need a group of 2, so we can multiply these two radicals. And so I kind of grouped it all together. I just said we would have 2 times 3. I put the coefficients using the commutative property. And then square root of 2 times the square root of 3. So our coefficients get multiplied and they stay as a coefficient in front. So 2 times 3 is 6. Our radicals get multiplied. They have to stay under the radical sign. So I still need a group of 2. Square root of 2 times 3 is 6. So in the same way that we combined our coefficients and then we combined our variables, we do the same thing with radicals. We have to do the coefficient part together, and then we have to do the radical part. Any questions for that one? Okay. When we are simplifying them, okay, simplifying means we're going to take out everything that we can possibly take out. So in this case, I've got square root of 120. It means I need groups of 2 of the same number. And so to do that, I'm going to factor 120 all the way down to the smallest factors. I use the little factor tree over here. And how you choose the factor in group is up to you. You just need to get groups of 2. So in this case, I ended up with, when I finished factoring down, I had 2 times 2 times 3 times 2 times 5. So I just lined it all up. I needed a group of 2, so here was my group of 2, and it escapes. It's the only part that can escape. So I have this 2 on the outside, and now everything that couldn't escape just stays underneath. So we get 2 square roots of 30, and that would be fully factored for a simplification for that one. So let's do this one. Square root of 64x squared. How could we rewrite this one? What factors, Jace, what factors of 64 do you want to use? If we're needing groups of 2, how would you rewrite this one? Yeah, 8 times 8. I'd use 8 times 8. Could we go all the way down to 2's? Yeah, we could do 2 times 2 times 2 times 2 times 2 times 2 times x, right? Is this a proper factor form of 64? Yes. And then we would say group of 2, group of 2, group of 2, group of 2. This one comes out as a 2, comes out as a 2, as a 2, as an x, and we would have 2 times 2 times 2 times x, which gives us 8x. Or we could do 8 times 8 times x. Here's my group of 2. It comes out as an 8. My group of x comes out as an x, and I have 8x. Same answer. You should always get the same answer regardless of how. This is just all the way down to the to the lowest factors. This is saying, I just need a group of 2. I'm going to find the biggest group of 2 that I can get it in. Okay, let's look at this one. Square root of 96x squared y cubed. What do we want to do for 96? What factors? You can use your calculator if you have one. Let's see. 96 divided by 3. 32. Okay, so I've got 3 times 32. 32 is 4 times 8. Or 16. What if we did 16 times 2? 16 is 4 times 4. So I could rewrite this as 4 times 4 times 3 times 2 x squared. What if I rewrite y squared times y? Does that give me my 3 y's? Yeah? So I need a group of 2, so my 4 escapes there. Do I have another group of 2? X squared, right? Comes out as an x. Y squared comes out as a y. So I have 4 on the outside, x on the outside, y on the outside. What's left underneath?
6y.
6y. Excellent. Okay, so we've simplified there. For 12a, square root of 12a, can I do anything to that? What can come out?
4 and 3.
Okay, so 4 times 3 times a. 4 is really 2 times 2, so it escapes as a 2. So I have 2 on the outside, and what's left in the inside? 3a. Right? And then 16, a to the 8th. How can I rewrite that one?
8 to the 4th times 8 to the 4th.
Yep, a to the 4th times a to the 4th. Excellent. And 4 times 4. Do I have groups of 2? Okay, that one escapes as a 4. A to the 4th, I've got 2 of them. Escapes as a to the 4th. So we have 4 a to the 4th. Is this one rational or irrational? Rational. Why? There's no numbers left in it. Fantastic. That one? Okay. Awesome. So we ended up with irrational, there's numbers left. Irrational, there's numbers left. Rational, there were no numbers left. And our first one was also rational. We ended up with 8x. So as long as there are no radicals left, we are rational. All right? Okay, so now that we know how to work with roots, what happens when your root is negative? Right? You're in trouble. Okay, when our root is negative, it ends up being a special term. So we are going to add those imaginary numbers, and I know we hit it just a smidge last week. Okay? The square root of -1 will be equal to the term I. I means it's an imaginary number. It has a special place on the coordinate plane. We're, instead of graphing x, y, and z, we're graphing whether it's just real or imaginary. So we're kind of grouping all those real numbers together. So you have a real part and you have an imaginary part. So we'll have real on the x-axis, imaginary on the y-axis. So we get to graph it as well. But I is a square root of -1. Okay, so if I is the square root of -1, let's work through this. There are 4 forms that you need to have memorized for I. They will always be exactly the same. It repeats in order. So if I is -1, I squared, we're just going to take, we have square root of -1 times the square root of -1. When any square root squared is just the base that's inside, right? So if I'm squaring the square root of -1, all I have is what's on the inside, so I have -1. So I squared will always be -1. So let's line it up, I cubed. Now I have I times I times I. So I have the square root of -1 times the I squared. Well, I just found out that I squared is -1. Right, so I can replace that. So I have -1 times the square root of -1, which I'm going to replace with my I. So I cubed is always -I. Any questions on how we got here? Okay, so same thing, I to the 4th. I would have 4 i's lined up, which I'm going to group differently into I squared times I squared. Well, I know I squared is -1. So I'm going to replace that. So I've got -1 times -1, which is +1. So I to the 4th is always +1. So those are the 4 factors of I that you need to have memorized and to know that. And there is, if you printed your complex number notes, anyone have your complex number notes? Print it out. Okay, I don't think it's on there. I have one of your homework sheets has this written on it as well. Okay. So make sure and have your notes out. And at the top it says, so as we have imaginary numbers, we're now going to end up combining them together. Okay. So now, if you have your complex number notes, make sure and have those pulled out. What happens when we start combining our real number system with our imaginary number system? Okay, so we know how to work with our real numbers. Now we know how to work with imaginary numbers that we can deal with square roots of negative numbers. So when we combine them, we get complex numbers. So they have both a rational and an imaginary part. So if I have 3 plus 2i, 3 is my rational part, 2i is my imaginary part, okay? And so this is the fun part. Actually, all numbers have both real and imaginary parts. Because if I have the number 15, it can be written as 15 plus 0i. So it can have an imaginary part, it's just 0, right? If I have only imaginary, it has a real part. The real part's just 0. Okay, so we can write all numbers as a complex number with both real parts and imaginary parts. Okay, so how does this help us? Or where are we going to see this? When you are multiplying binomials, and so you're working for a quadratic. So again, this is how it's tying back in. When we have a quadratic, if we had FOIL, we have 2 binomials that we're multiplying together, we're going to FOIL it just the same as before, right? So my first, I've got 2 times 1 here with the little green line, so I have the number 2. My outer, 2 times -2, I leave my I, so I've got -4i. My inner, 3i times 1 gives me my 3i. And then here we go, we have our last. 3 times -2 is -6. I times I is I squared. Okay, so now we're going to start combining and simplifying what we can. We can combine our middle terms because this is just like a variable, right? So -4i plus 3i gives me just a -1i. So we've got -i. Now, what do I know about I squared? I know that I squared is equal to -1. So anytime I see I squared, I need to replace it with the -1. So now instead of it being -6i squared, it's actually -6 times -1, which gives me a +6. So now I'm back to, oh, I have a real number in the front, and I have a real number in the back, which need to be combined. So we had 2 plus 6 gives us 8, and we leave our I part. So when you are multiplying binomials, we never leave our I in greater exponents than like the 1 that we have. Right? Any questions on how to multiply this? You have a homework sheet on multiplying imaginary numbers. Okay, so then how do we graph them? Like I said, on our coordinate plane, we have our x plane is all of our real number parts. Our y is our imaginary number parts, and we're going to read it like a coordinate. So for this first one, I've got 2 minus 3i. So how much do I have in my real number? 2. How much do I have in my imaginary? -3i. So I'm going to go over 2, +2, and I'm going to go to -3 in my imaginary. 1, 2, 3. So I would be graphed at 2, -3i. Okay. For the blue one, I have -3 in my real and +2i for imaginary. So I would go -3, 1, 2, 3, negative, and then +2 for my imaginary. Any questions on that one? Now on this one, 4i, what's my real number part? 0. So it's really 0 plus 4i. So my real number part is 0, so I'm just going to stay right there, and I'm going to go up 4. 1, 2, 3, 4. Here would be my graph for graphing. Any questions on graphing them? Okay. So that's our quick review on complex numbers, imaginary numbers. I'm going to hit back with quadratics, and we're going to do this one problem to see how quadratics help us solve a problem, and then we're going to go outside to gather data for our experiment and come inside and finish that, okay? So if you have a really fast racing car, I got a chance to see a Maserati and a Bugatti or something this weekend.
Electric?
Yeah.
McLaren.
It was so sweet. I'm like, that's a good looking car. McLaren, thank you. I voted for the McLaren over the Bugatti.
Okay. Did you see the other ones down at the bottom?
I didn't.
They were cool too.
Missed it. I do like cars. So if you're gonna find out, like, if you're a manufacturer or you're into racing and you want your car to go faster, it's like, what's the maximum speed that I can get out of an engine? So in this case, we had engine torque of one model of a car is given, and they gave us a parabola. All right, so if I'm just gonna quick graph this, what direction does it face?
Down.
Down, why?
Because there's a negative in front of it. -3.75.
Awesome, -3.75. Perfect. Okay, where does my vertex lie? What's that formula that we need to know. The x value of the vertex is at what? Negative b over 2a. Okay, so my vertex lies at negative 23.2 over 2 times negative 3.75, correct? Okay, so I'm going to end up with a vertex facing down. Let's think about what it's saying. It says x is the speed, so I have speed down here in revolutions per minute, and it's thousands revolutions per minute. And it says y is my torque. Right? Find the engine speed that maximizes torque. So I want the most torque for my engine speed. So what are they asking me for in this parabola? What number? What's the most important point that they're asking?
Are they asking for when x equals 0?
Okay. If x equals 0, that might be a place along the y-axis somewhere. If it's saying the speed that maximizes torque, so I want the highest value of y.
So the vertex?
The vertex. The vertex is my maximum, right? That is going to be the highest value on that entire graph. So if they've given me this equation, which equates to a parabola, and they're asking me to maximize something, the maximum value will always be found at your vertex. And then it says, what is the maximum torque? Well, that's going to be found in my vertex, and it's also going, whenever I have the highest, then it's going to have a speed associated with it, an x value associated with it too. So we always ask ourselves, what are we looking for when we're looking at this graph? I am looking for that vertex. Well, if they give me my equation, I can find the vertex because I know the x value of my vertex is equal to negative b over 2a. So if I plug in this information right here, so I graphed it here, the highest level is going to be our vertex. There. When I do it, I end up with 3.09 initially revolution, and so that's in thousands of revolutions per minute. So if I wanted it just in regular revolutions per minute, I've got to go over 1,000, right? So tens, hundreds, thousands, I'm going to add a 0. So 3,090 revolutions per minute is my x value. Okay. So how do I find my y value? The vertex of y is I'm simply going to take that 3.09 and plug it back in everywhere I see x, right? And when we solve for that, we get 74.7. So when my revolutions are 3,090 revolutions per minute, I'm at 74.7 torque foot-pounds. So let's kind of look on my graph. Oh, well, so I found my vertex the best I could with it, and I got 3.09, which was right where I was at 74.7. Okay? So there's my vertex. So that's how using this parabola actually gave us real information that was needed for it, okay? So another one, we have a shoe store. How do we put another real life problem into a quadratic? Okay, a shoe store is selling 200 pairs of shoes at $60 a pair. All right, so its revenue, its current revenue is 200 times $60. That's how much it's going to make, okay, a month. It says for each $1 increase in price, about 2 fewer pairs of shoes are sold. So how much per pair should they charge to maximize the monthly revenue? So we hear that word maximize again. We're going to end up looking for some sort of vertex, right? So I know that currently my revenue is 200 times 60 a month. So now we need to think about how do we get an equation so that we can find that vertex. Well, I wrote up here, we're going to tell the number of price increases of every time it increased by $1, we're going to call that N. So I increase it once by $1, that would be 1. If I increased it by $5, that would be 5, N would equal 5 for each dollar that we're increasing. So now my new price of my shoe is 60 plus N, which means my new number of shoes sold is 200 minus 2 times N, because it says every time my price goes up, the amount of shoes sold goes down by 2. So would that make sense? If my price is now $61, I would now sell 198 shoes. You see how I got these two equations? So price went up by 1 increment. My shoes has to go down by 2 for every increment. So now I have two binomials, which I can have an equation. So my new equation is 12,000 plus 80n minus 2n. We could rearrange that to do negative 2n squared plus 80 plus 12,000. And so I dropped that into our Desmos, and it gave me a nice curve. So they said, what is the maximum price that you should sell your shoes at to have the maximum sales, maximum revenue? Maximum revenue is going to be found where? At the vertex. Okay? So again, vertex negative b over 2a. So negative 80 over 2 times, here's my a, negative 2. So my vertex is found at 20. That means 20 increases. So I started where? I started at 60, and I increased it 20 times by $1 each time. So my new price is what? 80. So we found my vertex. And so at 20 increases, my new revenue is $12,800. So this is how our parabola gave us, I'm going to make the most money if I sell shoes for $80. Right? Make sense? Okay. We are going to head outside and gather some data with these two balls. What we're going to be doing is figuring out the velocity at which we can throw balls in the air and see if we can reach a certain height. Okay? So we're going to be throwing a ball up in the air and finding out, can we reach a certain height? Which ball goes the highest with the most velocity, and who can throw the most, okay? So we're gonna head out and gather some data, and then we'll come back in and do a quick review. Good one.
Let's do it.